just doing conditionally independent. So the x's, xi's are conditionally independent. Given y. So what does that mean in our Titanic problem, which is the problem we were working on? We sort of have two classes of people. We can divide everybody up into two things. There's people who survived. So survived. Actually, let's do survived equals 0 on this side and survived equals 1 on this side. That's the y. So y is either 0 or 1. And the point is, once you know if you survived or not, I'm going to assume all of the factors, all the data I have, all the x's are independent. So these are the x's. And there were different x's. There was like your age. There was like what class you were in. There was like the number of siblings you had, or like your fare, and so on. So actually, let's do age and fare first. Let's do log fare. And let's do what class you were in. This is like the number of siblings you had on the ship with you. And the same thing over here. Age. Log fare. Class. Okay. And so the naive Bayes says we're going to pretend all of these things are independent once you know if you survived or not. And that is super simple because things are independent. But it still allows the model to know some things. So for example, the log fare and the class are correlated, right? Because if you paid more money for your ticket, you're more likely to get a first class thing. How does our model know about that? Well, in our model, we're saying they're independent. So how could it possibly be that they're correlated? Well, they're lower for the people who died, and they're higher for people who survived. So even though we're making this conditionally independent assumption, we can still capture things that are happening in the model, and specifically in a way that captures what we want about y. So this is the naive Bayes assumption. There's a really famous quote you should all know, which is that, so I believe it's by someone whose name was Box, George Box, which is a great name. George Box famously, there's something called a box diagram, which has a box in it. And everybody thinks it's because there's a box in it. But it's not, it's because George Box's last name was Box. Okay, so George Box has a great quote, which is, all models are wrong. All models are wrong, semicolon. Some models are useful. Some models are useful. And I think the naive Bayes is a perfect example of this. This is clearly wrong. Like, of course, even if you know whether you survived or not, these things will be correlated. But nevertheless, this is a useful thing. It's simple enough that we can calculate stuff, and it's nice and easy to use, and it gives good classification predictions. So even though it's wrong, it can be useful. And that's what we're going to work on today. So in Mathematize, I was asking about how do we measure, or how do we estimate the parameters for these? So we're pretending they're all independent, which means each sort of blob on the board here has a different parameter we can estimate. We need to estimate these. Some of them are Gaussian. So for example, I pretended that the age, how old you are, and the log fare, I said those were Gaussian. Gaussian. And that's for both people. But things like what class you are in the first class, second class, or third class, you could pretend that that's like some kind of variable that takes on 1, 2, 3, but I just said let's make it Bernoulli. Are you first class? Are you second class? Are you third class? So these ones I split off into class 1, class 2, class 3. So maybe let's do, and this is really how it appears in the code. There's class 1, class underscore 1, class underscore 2. Are you second class or are you third class? Class underscore 3. And these things I'm sort of treating as Bernoulli variables. So they're either 1, you are in that class, or they're 0, you're not in that class. And so what I have to do is I have to estimate the parameters for all these three things over here. I got to estimate the parameters for all the things over there. They can be different parameters, right? Because survive equals 0 is different than survive equals 1. But I'm going to estimate the parameters and then use that to build my model. Okay. So class 1 and so on. Over here again. Same thing. So that's the setup of the naive Bayes. Any questions about the setup? Yeah.
Sorry, I think because we actually know the class of people who are in the ship, and we use this as dynamic variables.
Right.
So I'm wondering why we are going to predict them.
Okay, so the whole point is I'm building a model. So I'm building, you can think of what I'm trying to do is I'm trying to have an accurate understanding of the probability of x given y. This is I'm trying to come up with a formula for the probability of x given y. So given that you survived either 0 or 1, what is the probability that your age comes out to a certain number and you're in second class and whatever, right? And once I have the probability of x given y, I can do the discriminant thing with Bayes' theorem that we did last time to turn that into the probability of y given x. So we're just building up the probability of x given y, and then we're going to do our flip trick to get classifying. Yeah, that's a good question. Okay. Any other questions about this setup? Okay, so let's see what you guys said in Mathematize. So the question was, what do you need to do to measure the mean and for these things? So for Gaussians, you got to do something. For Bernoullis, you got to do something else. What do you have to do? That was the question. And let's see what you said. So, all right. So for Bernoullis, lots of people said just the mean. Some people said, or one person said both the mean and the variance, or one person said something else. And I think the correct answer is just the mean. That's totally fine. And the reason is Bernoullis only have one parameter, p, and p is the probability you're 1, and 1 minus p is the probability you're 0. So if you take the average value, that's also going to be p. So if you take the mean, that'll be an estimate for p. So maybe I'll make a little chart here for the parameters to estimate. Parameters. And for Bernoullis, you only have one parameter, that's the parameter p, and you can estimate it just by doing the mean. I will point out that class 1, class 2, class 3, you can think of them sort of individually as Bernoullis and measure their individual p-values, but you know that you were in one of the classes for sure. So they're sort of related, like this p-value plus that p-value plus this p-value will add up to 1. Some people call that a multinomial, and we'll talk about this a little bit. But in terms of estimating, you can think of each one has one p-value, and you just got to estimate that p-value, and you do it by taking the mean. Let's see what happens for Gaussians. For Gaussians, you guys are right as well, that you need to do the mean and the variance. So Gaussians have two parameters, the mean mu and the variance sigma, and you gotta estimate both of them. And this is all the stats stuff that you guys did in stats, right, about Gaussian distributions, T distributions, stuff like that. Okay, but we're gonna estimate these things. We're gonna estimate the mu's and the sigmas for all these guys, and then put them all together to make a model. So that's what we're going to do in the code here. And where was it? Okay, so this was last time we did it with logistic regression. We got these nice curves, and now we're doing it with naive Bayes. And let me open it in Colab as well so we can run stuff. Let's do one of each. Okay. So I want to go down to the naive Bayes model. And so here are my little commands. And in this block, we're calculating the mean and the variance of all the Gaussian-like variables. And the Gaussian-like variables, I said, are age and log fares. So I have a list with the Gaussian variables called my Gauss vars or something. Let me see. Where did it go? Let's open it here so we can query stuff. And we can use the table of contents. Naive Bayes. So we're calculating stuff for these my Gauss vars. This thing. So if I add a code block and say what are the my Gauss vars, please print them out. I'm just gonna make sure that it is what I think it is. Did something break? Okay, it doesn't have the file. Okay, give me 1 second, guys. I'm gonna load up the file. Okay, so I uploaded the file. Let's try again. And now we can jump to naive Bayes. Okay, so the two variables in my Gauss variables are age and log fair. So I'm pretending those are Gaussian. And so for those ones, I got to estimate a mean and a variance. And what I do is I just look at the two different classes. So just like I have on the board, I split everybody up into two. And so you can either be in y equals 0 or y equals 1. And then I'm going to do the means and the standard deviations for those things. So I go through all the possible things on the board, 0 and 1. And then I loop through all of these features, the age and the log. So there's 2 for loops. And then I do the mean of everybody who has that feature. So I take the vector v as everybody who survived or not, and I do the mean of their ages, the mean of their log fairs. I do their standard deviations, and so on. And then at the end, I get this nice little thing, which is the result. So of people who survived equals 0, their mean age was 30. Of people who survived equals 1, their mean age was only 28. So it's pretty similar, not a huge difference in this case. But what it does tells me if somebody is older than 30, then they're more likely to have survived equals 0. If they're younger than 28, they're more likely to have survived equals 1. Right? And that's going to be built into our model according to a Gaussian distribution. You also calculate their standard deviations. And then I did the same thing for log fair. So remember, the log fair is the log base e of how much they pay for their ticket. And this is a bigger difference. So people who survived equals 0 paid 2.7, and people who survived equals 1 paid 3.3. So if people paid more for their ticket, that means they're more likely to be in the survive equals 1. And if they paid less for their ticket, they're more likely to be survive equals 0. So when we do Bayes' theorem, that will be taken into account. All right. Questions about that? So far it's with Gaussians, and I'm going to do the same thing for the Bernoullis in a second. But the setup is okay? Okay.
I have a question.
Yeah.
So the purpose of us doing this in different ways is to evaluate how well the model.
Yeah, so at the end, at the very end, I'm gonna have a classification. So right now we're developing probability of x equals y. And then we're gonna do this discriminant thing to get the probability of y equals x. And we're gonna compare it to how did it do against logistic regression using the exact same variables, right? And this is sort of like the most simple thing you could do. You could do something more complicated. Like for example, if you wanted, you could like calculate how these things depend on each other. Like you could say instead of these two things being independent, they could be a two-dimensional Gaussian with a covariance, and I'm assuming the covariance is 0. You could calculate the covariance and do that. So this is like the simplest possible thing, and I'm going to show you at the end that it does almost the same as logistic regression. It does like a little bit worse. Yeah, that's where we're going to get to. Yeah, great question. Okay. Okay, so same thing for the Bernoulli variables, or the Bernoulli-like variables. And okay, what are the Bernoulli-like variables? Let's print them all out. So print my Bernoulli variables. And this is why I like using Python, because you can put things in lists and stuff. Oh no, you got to spell Bernoulli right. It doesn't work. So there's P class 1, P class 2, P class 3. What class were you in? 1, 2, or 3? Sex male, sex female. Were you a male or a female? P arch is like the number of parents you have on board, either 0, 1, 2, 3, and so on. So all these things that are on the board that I got from the dummy variables. So they were originally like grouped together, but I just split them off into these dummy variables. Okay, and then I do the same exact thing. So I just loop through the two different survive equals 0, survive equals 1, and I calculate the average in each one to get the p-value. And you get this big thing that looks like this because there's a lot of them. So of people who survived equals 0, 14% of them were in first class. But of people who survived equals 1, 40% of them were in first class. So that p-value difference can be used to sort of tell the difference. Right? If somebody is in first class, they're more likely to have come from survived equals 1 than survived equals 0. So that's exactly how we're going to use this. And it's just a simple average in this case. You can do any fancy statistical technique you have to estimate parameters you can do here. I'm just doing the simplest possible thing. And now we have a dictionary with all of the means and variances for the Gaussian stuff and all of the p-values for the Bernoulli things. And now what we got to do is probability of x given y is just going to be the product over everything. So the probability of x given y is going to be the product over everything, and then we're going to do the log. And when you do that, you're going to get the log likelihoods. And now we have a little conundrum here, because I have three things, right? I have class 1, class 2, class 3, and they add up to 1, right? They're related. And we never did that in class. So in the videos I did online, I talked about a 0 or 1 value thing, and this is sort of like there's 3 categories you can be in. And we estimated the p-values, but we need to know what is the likelihood. So that's the next question on Mathematize, is what is going on with the likelihood for this thing. So for a Bernoulli, if it was literally just 0 or 1, you can use this formula, which is y log p hat plus 1 minus y log p hat. Right? So we've already gotten the p hats. These really should be hats everywhere. That's what we just estimated. And now we're going to take a real data point y, and we're going to calculate the log likelihood to decide, is it more likely to be survive equals 0 or survive equals 1. And this was the formula we used before. Oh, I'm missing a 1 minus. It should be y log p hat plus 1 minus y log of 1 minus p hat. But now we have 3 numbers, and the question is, what should the formula be? So we're going to derive it in a second, but I'll give you a chance to look at 3 options here first. One of these is correct. And I want you to think about why. You might need a pen and paper to figure out, for this 3 class P thing with class 1, class 2, class 3, which of these formulas is right. Okay, it's pretty washed out on the board, or on the TV, but you can try to look maybe on your computer and figure out what you think is correct. So I'll erase the board and write exactly what we're doing, and we're going to derive one of these 3 formulas to use in our calculations. Okay, and I want to hide results. Maybe I just want to zoom out. Okay. Okay, so this is the setup that we have in this problem, and we've already done the 2 class situation before, so that was in one of the videos. When you have 2 classes, the probability that y equals y, it's this p hat to the y times 1 minus p hat to the 1 minus y. So it's either p hat or 1 minus p hat, depending on if y is 0 or 1. And then when you take the log, you get the sum of 2 terms that is like the cross entropy loss. Now we have 3 classes, so we have vectors now. So instead of having a p and a 1 minus p and just one number, we have 3 numbers, p hat 1, p hat 2, p hat 3, and we have encoded our observation, instead of it being 1, 0, it's a vector with one of the components equal to 1 and the other 2 equal to 0. And the question is, how do we write down the probability? And the thing that's nice is the same kind of formula works, but instead of p hat and 1 minus p hat, you have 1, 2, and 3. So you have p hat 1 to the y1, p hat 2 to the y2, p hat 3 to the y3. So this is the thing to realize, that exactly one of y1, y2, or y3 is equal to 1. So if you make this formula, 2 out of 3 of these exponents are going to be 0, and then that's going to just be a 1, and it's going to disappear, and you're going to be left with exactly the p hat that you want. So just like before, there's this trick of writing the probability like this. So, you know, this is the same thing as p hat 1 if y equals 1, y1 equals 1, p hat 2 if y2 equals 1, and p hat 3 if y3 equals 1. So same thing as before. And now you have to do the log of that. It's a log of a product. The log of a product is a sum. So what is the sum going to be? It's going to be the sum of yi log of p hat I. So because this is a product over three things, you get a sum over three things at the end. So let's see if you guys got that same thing. All right. So about half the people got it, and half the people were tricked by this 1 minus p hat. So this is the thing I think to watch out for, is before there was a 1 minus p hat, it was really like a 2-class thing, and we were like, oh, 2 classes, well, then we only need to keep track of one number. So we did like this shortcut of writing 1 minus p hat for p2, and now where there is no 1 minus, because p2 is like, we're enforcing the fact that these are all sum to 1. So you could, if you wanted, you could do a shortcut and write a 1 minus p1 plus p2 for p3 or something, and then you'd have a funny formula where p3 is 1 minus p2 minus p1, but we're going to do it this way. So this is the thing I want you to watch out for. When you switch from 2 to 3 classes, you often have a slightly different looking formula, even though it's the same exact math. Any questions about this one? So this is like multi-class cross entropy or something like that. And that's exactly what we're going to use to calculate the likelihoods. Okay. Okay, so here's the formula where we compute the likelihoods. And when we do the likelihoods, there's 2 terms. So this n and LL is the negative log likelihood. And what we're going to do is for any given, let's see, what are we looking through here? Give me 1 second to read this code and figure out what's going on. Means of I. Okay, all right. So what we're doing is we're taking the original data set and we're calculating at the same time, we're calculating the probability or the negative log likelihood for both classes for every given point. So let me write on the board what we're doing. So we're not using this 2-class thing. We're going to use this 3-class thing in a sec. I'll try to leave that up. So for every observation x, we compute the probability of x given y equals 0 and probability of x given y equals 1. So what we do is we computed the means and variances for both classes. That's what we already did in the previous block. And now we're going to compute these 2 probabilities. And these probabilities, we're actually going to compute their logs, because that's what we actually need. So we're going to do the negative log likelihood. The negative log likelihood. And because we're assuming things are independent, we're doing this naive Bayes assumption. When you do the negative log likelihood, that is a sum over all the variables, right? Because independent means product over all the different things. That's what independent means. And so when you do the log, it's a sum. So this is equal to the sum over all variables. And then it's the probability, the log probability minus the log of the probability of xi for that feature. So let's say I is the sum over all variables. Xi equals x given y equals 0. And the same thing for y equals 1. Okay. So this is the nice thing about naive Bayes. You can just do each feature independently and add them up. And that's what we're doing. So let's go back to the code here. So what are we doing for the things? So I do it in 2 parts. First, I add up all of the ones that are Gaussian. So this is a sum over all the Gaussian type variables. And I'm doing exactly the kind of squared formula for a Gaussian. So it's the actual value minus the mean divided by the standard deviation squared, right? That's the log in a Gaussian. So this is sum over Gaussian-like, and you do xi minus the mu I divided by sigma I squared. And then you do the same thing for all the Bernoulli types. And this is where we're going to use this formula. So for all the Bernoulli variables, you're going to do this thing, xi times log I over all the possible Bernoulli things. I think this one has a minus. Okay. So there, this term is the term for the Gaussian stuff. I forgot the factor of a half. And this term is the term for all the Bernoulli stuff. That's this line. And this is the formula where I'm using exactly the formula we just derived, which is the value yi times the log of p we estimated in the previous block. Yeah.
So if you had a separate Bernoulli variable that only had two classes, would you have to attach a third term onto that to represent that third class?
Yeah, so this is a fantastic question. So it depends entirely how you're representing it. If you're representing it as two different columns in your thing, and it's 0, 1 or 1, 0, and you're sort of like writing everything down twice, then you don't have to do anything. Then it works as written, because you have a P1 and a P2, and you're doing y1 log P1 plus y2 log P2, and it just so happens that P1 is 1 minus P2, and vice versa. However, maybe you have an economic data frame where you're like, I want to save columns. So instead of having two columns where it goes 0, 1 and 1, 0, I've deleted the rightmost column to save a column, right? Because you can recover it. Then you would need to sort of put it back in as a 1 minus P. Yeah, and that's exactly the difference between 2 and 3 columns. So naturally with 3 columns, you sort of keeping 3 doesn't seem like a waste. But of course you could delete that last column and recover it by the first 2, and then you'd have to do a little extra step. But the way I've done it is a very simple formula. There's no 1 minus P's or anything like that, and it really comes from this calculation.
So if you had 3 classes and you weren't keeping that last column in the data set, how does the formula?
Yeah, so then you would have to add in a term. You would have to add one in that is log of 1 minus P1 minus P2.
Okay.
So you sort of have to pretend, you'd have to recover and put it back in.
Yeah.
Which actually, so the other advantage if you do it this way, if you have some kind of process that is selecting variables, then it's more convenient to do it this way and have all 3 columns and then have the computer say, oh, actually column 3 is not that important, let's delete that. And then you still have all the information from column 1 and 2. Versus if you only have column 1 and 2 to begin with because you already deleted column 3, and now the computer comes along and deletes column 2, then you're never getting it back. So in a lot of ways this is more convenient, and the only disadvantage is that you have an extra column, but computers these days are good at thousands of columns, so you shouldn't worry too much about that. Yeah, great question. Okay, so we're adding up these things. We're adding up all the Gaussian ones, we can add up the Bernoulli ones. The other thing you can do is you can say that some are more important than others, right? This is something you can always do. And here I made all the Bernoulli ones twice as important. That seemed to make things work a little bit better, right? And which is kind of saying oh, maybe some of these are noisy, we don't trust these as much, and this is the one we want to focus on. So you can artificially add some factors. So you can multiply everything by 2 here, say, and that's just saying make this twice as important as that. But at the end of the day, what you get is a discriminator, which is the difference of the 2 log likelihoods, right? So what is the difference of the log likelihood that you're class 0 minus the difference that you're class 1? And from all the stuff we saw last class about discriminators, if you do the sigmoid of that, then you're going to get a probability of y, right? So this is by Bayes' theorem. This is what we did last class. Bayes' theorem. Bayes' theorem. So far everything has been the probability of x given y, but now by Bayes' theorem, the probability of y given x, it depends on these 2 things, and we saw last class it's the sigmoid of the difference of the log likelihoods. So it's the probability of x given y equals 0 minus the log of the probability of x given y equals 1. So it's the sigmoid of the difference of the logs. So we calculate these 2 things for each class, we subtract them, we apply the sigmoid function, and now we have a probability of being either you survived or you didn't. And so this, at the end of the day, we get an output that is exactly very similar to logistic regression, right? So in logistic regression, which is what we did last class, we had an output which was this I called it this LR probability. Logistic regression probability. For every single person, we say what is the probability that they survived or didn't. And at the end of the day, in this naive Bayes calculation, at the very last second, we take all the information we have and we combine it into one number, the naive Bayes probability that you survived or you didn't. And just like before, you can make a ROC curve for this that tells you the trade-off between people you've labeled, like, you know, true positives and false positives, according to you labeled them as having died and they didn't die, or vice versa. And you get a curve that looks almost the same. So you get almost the same exact answer as before. So this was what it was before. This one is a little bit better. The area under the curve is 0.86. And here, the area under the curve is 0.83. So not that different. And you can also compare directly. So here is a scatter plot comparing the two probabilities. So LR probability is from logistic regression, and NB probability is this naive Bayes thing. And you can compare them and see what the differences are. And you can see that both of them do quite good. So the blue and the orange are the true classes. So blue means you actually died, orange is you actually survived, and both of them do a pretty good job of separating people. If you have a low probability assigned, then you probably survive equals 0, and if you have a high probability assigned, you probably survive equals 1. But you can see like, there's like these like kind of false positive bumps, right? Where these people they were assigned a pretty high probability, but they did in fact die. So that's not good, and you can compare the scatter plot and see what the differences are. And they're really somewhat similar at the end of the day, which is surprising because they're two completely different methods. Okay, I'm gonna leave it at that. You guys can stare at this on your own. Again, it's on the course GitHub and everything, and you can take a look. Any questions or comments about this naive Bayes discriminator method? So this is a way of combining Bernoulli and Gaussian variables together, and it's sort of like in the textbook they talk a lot about the linear and the quadratic one, which is only Gaussian, and this is some kind of more general stuff. Yeah.
So one general question. You know, we first started with regression,
Right.
and then we go to classification.
Yeah.
With logistic regression, and then we started learning Bayes theorem.
That's right.
And the first, sample of Bayes theorem is like the simple one we've got here. Am I right?
Well, so we did it before we did this. We did it just for Gaussians, right? And when it's just for Gaussians, you don't have this extra Bernoulli stuff, so it's even simpler, right? So we did that in one dimension, and then this is one way to multi-dimensionalize, right? How do you go from one dimension to many dimensions? Before we only had this one term, and now we have this term is sum and this term is summed. So this is like the first multi-dimensional example we're seeing.
Yeah, but naive Bayes is the first class of Bayes theorem classification. And
Well, I would say that even in one dimension, like the things we were doing in Desmos with the line, I would say that still used Bayes theorem. It still had this like sigmoid, right, of the difference of the probabilities. It's just that the probabilities only had one variable. So you didn't have to assume some independence or something to get them all. Whereas here, there's many x's, and so we had to use naive Bayes to try to estimate them. You could estimate them all together, right? You could like have a big, instead of having 7 p-values, you could have like a 7x7 matrix of all the like correlations. So you could do that as well. But then you start to sort of run out of data, right? Yeah. This is a very good question. So because your next project is going to be a classification project. And so Kaggle has, there's the Titanic, but there's also, they made something called the Spaceship Titanic, which is like a bigger Titanic data set. So there's like, I think it's a fake data set because it's about a spaceship and people getting abducted by aliens from the spaceship. But it's like exactly the same kind of thing. You have to predict who survived and who didn't. And I want you guys to work in pairs for this one. So you'll work with a partner and you're gonna do both. You're gonna do logistic regression and some kind of discriminator. And just like the first project, it's going to be pretty open-ended on what exactly you want to do. So it's the same kind of theme that's been going on in the course. We do a lot of theory on the board in class, and then you guys do practical things on the project. And that'll be posted. So the draft is due 2 weeks from the coming up Sunday. So it's like in 3 weeks, a little bit less than 3 weeks. And I'll post like the details sometime soon about that. But this is a good time if there's any like questions or comments about something for that project. You can ask now. Okay. Yeah.
In particular, I wanted to ask about the videos with another project.
Mhm.
In video, they talked about cross-validation,
Yeah.
and they said they spoke about a very popular mistake.
Yeah.
Before selecting,
Right.
the variables, we should implement, let's say, cross-validation,
Mm-hmm.
and okay, not vice versa.
Right.
But I didn't get it completely because if we go through cross-validation at first step before removing some variables,
Mm-hmm.
then we will predict based on those, and then we will check the minimum RSS maybe to choose the best model. Okay, what is the next step? So because we did it in the first step, everything. So
Yeah, okay, this is great. So yeah, we're just finishing up all the stuff about classification. Now we're starting exactly your topic, which is on cross-validation and that kind of stuff. So this is the next chapter in the book. And so this is the notebook I had on cross-validation that we're going to look at. And yeah, but let's talk about this issue from the videos first, about when do you apply the cross-validation, right? And what they are saying is you should apply, anytime you make any kind of choice, you should cross-validate that, right? So the example they had in the videos, yeah, so this is a very good like real world example, right, of like real like medical people making statistical errors and things. So there was two options for your cross-validation. So option 1 and option 2. Okay, so in option 1, this was I guess the mistake. You choose variables first. And then you use cross-validation to estimate RSS or MSE. So you choose the variables and then you use cross-validation to estimate the error that those variables would give you. And then the other option is you do cross-validation first. So cross-validation first. So first you divide up into 5 sets or whatever, and then you use those sets, then you choose the variables based in each set. Choose variables. And then you do the last step of get mean squared error, right? Okay, and here is I think the big difference between these two. In this one, you're choosing the variables first. So you have one set of variables that you're always using. So here it's always the same variables. Whereas in this one, because you're doing cross-validation first, when you choose the variables within each set, it is not necessarily always the same. So I think that's the big difference. And in fact, so the examples they were given where this goes horribly wrong in the video, they were saying like imagine that the variables have nothing to do with they're independent of the outcome. So you just have a bunch of noisy variables, but you've got a lot of them. So just by chance, it looks like some of them are important. And so in that situation, you're going to have these noisy variables that you're using here. But what's going to happen over here is you're going to have a different set of noisy variables for each one, because like every time you have a new set, which ones are important for that particular set will be random. And so you'll get completely different sets here. So even if you don't even do the last step of calculating the mean squared error or the like you don't use it to estimate the error. You just look at, did I choose the same variables? That's going to tell you something important, right? In this one, you can't look at anything. You only have one set of variables. But over here, you can be like, I ran this 5 times, and every time I got a completely different set of variables. So maybe these variables are not that helpful, actually. Yeah, so that I think is the big difference. We can talk about how calculating the mean squared error happens. But what was your original question?
Yeah, you know what? I actually understand the difference, but
Okay.
the problem is this. Let's say we are going to remove variables based on the correlation between
Sure.
themselves.
Uh-huh.
So at first step.
Uh-huh.
Then, option 1. So, and then we do cross-validation. Okay,
Right.
this is clear. In the second one, we will first do a cross-validation, and then we will, for each attempt we've
Yeah.
got, we will have different variables based on the correlation between themselves. Am I right? And then
Yeah.
we will get different variables
Right.
based on the correlation, and
That's
we
right.
cannot proceed in this way.
You cannot what?
Proceed, to get the MSE, because in each attempt we get different variables, so we cannot understand in the end which one we choose.
You're saying you're saying at the very end of the day, which variables do you
Yeah,
choose?
yeah.
Yeah. So again, the cross validation you should think of in the part of your brain where you're just trying to validate how good your method is, right? And you should think about this as a separate. Everything going on here, both options are a separate step than making the best final model you can. So in cross validation, again, you're just like all validation methods, you're not using your entire set, right? You're using like 80% of your training set. So whatever you do this way, you should think of it as like an experiment to decide what you're actually going to do. And so after you decide what you're actually going to do, you decide based on whatever method you used, you decide I'm going to use 10 variables. Then you should go back and do this 10 variable choice with the whole data set. So either way, whatever the conclusion is, you're gonna have to redo all your work anyways. So the fact that it's different variables in each one doesn't matter for the final answer.
So the number of variables matters.
Right. So or whatever you want to choose. Yeah. So yeah, exactly. I think the number of variables. And again, the way you're going to choose it is at some point you're going to have a test and a train graph, and the test error is going to go like this, or the training error is going to go like this. So this is the training error with the number of variables on the x-axis. And the test error is going to have something like this, right? The test error. And you want to pick the sort of the minimum of the test error. Yeah. So you're gonna choose this number of variables, and then you're gonna redo everything.
Thank you.
Yeah. Yeah, that's a good point. So yeah, I didn't really understand why they made such a big deal about this, but I guess they must have had some experience with some like real world people who were doing it this way and not that way, who are getting some wrong answers. So maybe it's important in practice. But yeah, I think the big difference is exactly this: the fact that if you're getting different variables every time, that's a good indication that the variables there's something wonky going on. Okay, yeah. Any other questions from the videos? It's great.
Okay, but I think it is probable that we get different variables in option 2, but let's say, okay,
Yeah.
we got different variables.
Yeah, I think it's like a spectrum, right? So sort of like if you're getting mostly like, like as you add in more variables, if you always add in the first 3 and then the fourth one is slightly different, then sure, like that's kind of to be expected. But if you're getting completely different variables every time, then it's telling you something. So it's true, like if, and if things were perfect, if there was no like sort of noise in your data set, you would get the exact same thing every time. So yeah, it's true. It's kind of a complicated thing in practice. Yeah. Okay, so what I have in the notebook is basically, we won't spend too much time on it, but we basically have some real life graphs like this that I wanted to show you guys. And this is the data set on cars. So we have a bunch of different cars, and we're plotting their horsepower versus their miles per gallon. So the horsepower is on the x-axis, and their miles per gallon is on the y-axis. And you can see the cars that have like a horsepower of 50 have terrible miles per gallon, right? This is kind of like maybe the opposite of what you would think, right? Maybe a car that is like not very powerful, maybe it has very efficient. You can make it efficient, right? Because you don't need to make it powerful. So you're the engineer, you're designing the car, and you're like, should I make the car efficient or should I make it powerful? And you're like, well, I can make it really efficient. But that's not what happened, right? It's the opposite. Does anyone know why this is maybe the case? You think of why the really wimpy cars are also really sucky?
But that's the miles per gallon, right?
The miles per gallon.
So the higher the miles per gallon, the more efficient. The
Oh, maybe maybe that's why. Okay.
right?
That was not what I was thinking, but yeah, that might be why. Yeah, I mean, I was thinking of gallons per mile. Okay, good. That's also done. Okay, yeah. All right, good. So the thing that is not shown on this is when the cars were made, right? So some cars are older than other cars. So this is what I was thinking, is that the older cars are more likely to be crappy, and then they have worse miles per gallon. But okay, it's actually fine. Is there an age category? Now I'm curious. Okay, well maybe I'll go explore it on my own time. But in this one, we're deciding how should we fit a linear regression to this, and should we use a line or should we use a polynomial? That's the question we're going to ask. So what power should we use? So we're always going to do just this one graph, horsepower versus miles per gallon, and we're going to either fit a line or a quadratic or a cubic or what, and we're trying to see what's best. Okay. And I split it up into a couple parts. So the first thing is ordinary validation. This is what we've been doing. I think I might have called it cross-validation by accident earlier in the course. But ordinary validation is just you split into a training set and a test set, and you just do it like that, right? So you just have your training set, you do everything on that, and then you just test on the test set. That's the sort of typical way. So you have x train, x test, y train, y test, and you do the thing, you just get the models. So here's linear, here's quadratic, here is cubic, and here is degree 4 and degree 5. So lots of different ways you can fit it, and you can see it gets kind of like more fancy, right? Like for degree 4 and degree 5, you have this funny little uptick at the end that is starting to be there. And I've computed their train and the test error. And this is on a split. I've just randomly split the points into two, right? Either train or test. I think that is a parameter you can pick. Here I've done it with test size 0.5. So half the points are training points, half the points are test points. You could do like 80% is more common. But you have a test and a train. Okay. And what you get, if you make a plot, you get something like this. So this is a plot just like the one I have on the board. But what I have done is I have done it 5 times. So here I split it up once, and I just ran the model once. So like the test errors you see are for all the same test and training set. And here I did it, I generated a different test and training set 5 times, right? So when I split the points in half, there's like a billion ways you can decide these ones are the test set and these ones are the training set. And here I've done it randomly 5 times. And I think the thing to notice is that there's a big difference between one run and another one. So like in this run, we thought the error was like 24, but in this run we think the error is like 16. And so I think this is the takeaway that they mentioned in the video, but didn't spend a lot of time on, is that you really get huge differences just depending on random chance. So if you're trying to use the ordinary method, this is why I call this the ordinary method, you're sort of quite subject to luck of how things got divided up. And here actually the test set is 0.9. So I'm using 90% of the set as a training set and 10% as a test set. So I guess the label is backwards. But where is it? Yeah, my test size is 0.9. Oh, okay, that's kind of a funny thing. Maybe it should be like 0.1. This is kind of backwards, but okay. What is the thing that is the same for all of them? So the first thing to notice is it's quite different, but all of them, if you look at the test error, that's the red, it all has a minimum at 2. And this is the thing we're using it for, right? So we're trying to decide which one we should use, and we're going to go back and do it with a polynomial of degree 2. And so even though they're quite different, you always get the same answer, which is that minimum is 2. And so don't fall for the fact that these go down, right? The blue curves go down at 5. That doesn't matter. That's the train error. That's exactly this thing that's going down as you add more variables. The thing that matters is what is the minimum of the test error, and that's always at 2. So I think what is the moral of the story? If your job is to just decide the number of variables or which variables or something like that, then this is perfectly fine. Just take the minimum of this. If your job is to actually estimate what is the error, this is not great, right? Because it's moving a lot. Okay, and we're going to get down to k-fold cross-validation, which is a lot more accurate for doing that. So one way to do it would be just to average these blue curves, you would get something more accurate. But if you do it just once, it's not that great. And the k-fold cross-validation is exactly some kind of averaging, but being careful to not use the same data twice, right? That's exactly what it is. Any questions about this one? So yeah, you guys we've sort of seen this already. This part of the course is a bit of a repeat of something we did earlier. So we won't spend too much time on it, but yeah.
So these 5 sets are linear, I mean not quadratic or degree 3, 4, 5. They are degree 1. Am I right?
So the x-axis is the polynomial power, and the y-axis is the error. So what it's showing you is that degree 1 you get an error, which is usually 24 or 25. Degree 2 you get this really wide spread between 16 and 24. But in all cases it's sort of less than the degree 1. So it's saying the quadratic always seems to fit better than the linear one, no matter what you use. So the quadratic is always a bit better than the linear. And then what you see is that if you compare cubic to quadratic, something interesting happens. If you compare cubic to quadratic, the training error is always like flat, like the training error doesn't get worse, but the test error does get a little bit worse. Right, so you're starting to go up. And that's showing you that once you go to cubics, you're starting to overfit a little bit. And then the overfitting gets really bad as you go to 4 and 5, which you wouldn't see otherwise.
Yeah, but the question is, do we usually estimate the error by this graph? Because we just select the degree and then go to the full data set and estimate.
Right. So, and when you go to the full data set, you're not producing an estimate of the error at all. But you submit it to Kaggle, and then Kaggle tells you the estimate of the error, right? So I think this is part of the point, is that a lot of the times your job as a data scientist, you don't have to estimate the error. You just try to do your best, and you're not telling anybody how good you're doing. You're like, I think this is the best. Let's try that. Like, that's what you do, and it's good for that, right? So 2 is the best, and we'll just try 2, but we don't know how good it's doing. And we're going to see, actually, next class, we're going to learn this method called the bootstrap that is better for that. Yeah, so we're going to do that at the end of today, maybe a little bit, and next class. But yeah, so I think this is the moral of the story. This is great for deciding what to do. It's not great for knowing how close you are. Okay, so what else is in this notebook? I did the leave one out, cross-validation as well. And this is all taken from, there's somebody who took all of the labs that were done in the textbook and the videos and converted them to Python. So this isn't my code, this is somebody else's. We did that, and so this is like one way to do this leave one out. And I think there's even there's a function in scikit-learn leave one out that is being used. So these things have been implemented, and you can use them. And what you can do is you can figure out that the leave one out error is like 24.4 for linear, which is right around the average of these. So it's not so surprising that you would get, when you do the leave one out error, that's like a k-fold cross-validation where k is as large as possible. And you get some kind of average of all of these things. Okay. All right, and then they do the same thing where they're comparing the different polynomials. So they're doing it for linear, you get 24.4. For quadratic, you get 19.24. And let's go see, is that approximately the average that we got? So here we got from 16 to 24, the average 19 would be around here. It does look like the test error is highly concentrated around this 19. So that's kind of what you're getting. And so leave one out can be a reasonable way to estimate these things as well. Here it is as a plot. And you can see that 2 seems to be best, but look, something funny is going on 5, right? So it seems to think that 5 is better than 2. But if you have this thing where you're going up from 2 to 3 to 4, you might not want to trust that 5. It's just a little bit, you have to do some interpreting to figure out. Okay, that's leave one out error implemented in case you ever need to look at that. And here they do k-fold cross-validation. You get something very similar with the same kind of thing. It's almost the exact same numbers. And in fact, it does do the same thing again where it goes down at 5. So you have this other thing where you're at 5, you're starting to go down. Even though I think it's important to always look at the train error and see what is the training error doing. And it really is taking a big step down, and the test error goes up sometimes. So you got to be careful with these things and decide if you want to do 5 or not. And I won't spend too much time debating this. You can think about if you would do polynomial 5 or would you do polynomial 2. I would say polynomial 2 is more trusted than 5 here. Okay, so that's basically it on validation and cross-validation, which we talked about earlier in the course and was in the videos. But I think you guys have gotten the message about that for the most part.
Yeah, one more question
Yeah,
about video. You know, the guy, I mean, I forgot the name, but he said it is going to advisable to choose either 5 or 10
Folds.
folds.
Yeah.
But at first I thought he said 5 to 10.
Yeah.
But in the end, I was wondering why 5 or 10.
Yeah, I think there is no right answer, and I also think if there was a right answer, it would change over time. So when those videos were made, running a lot of folds would really take a lot of CPU time. Like if you have a big data set, you want to run it in 10 times, then you're really talking about running your program for a long time. Nowadays, computers are faster, but also the data sets are bigger. So like, can we still run 10 or should we run 100? Like, this is a thing that happens. And I'll tell you, in my research, I work with neural networks often, and I talk about the uncertainty in them. And those really take a long time to run. So like if you run 1, you're just like, I ran 1, I got this answer. You're like, okay, can we run it like 5 times? We're like, yes, but it'll take 2 weeks. So like, do you want to wait for 2 weeks to run 5 more models of the copies of the same thing? Or do you want to just like go with the 1 and do what you can? So it really depends on the domain. I don't think there's a right answer, like always do 5, always do 10. You just have to decide based on reality. 5 is a good ballpark figure, I think, like to roughly know. Yeah. Okay. So what we want to get to, and I know you haven't seen the videos on the Bootstrap yet. Those are due next class. But I want to show you a problem that the Bootstrap solves. And it's a very easy to understand problem. And at the end of the day, we're going to get to the Bootstrap, and that'll be next class. But we're going to start it today. And it's a very simple problem, which is you have a bunch of uniform random variables. So variables between 0 and 1. And you want to know what is the median. Okay? And you can imagine this is like in real life. If you have a sample and you take the median, you want to know how close is the median to the true population median, right? So like a good example would be, if you want to know the median salary that somebody makes, how many people do you have to sample before you're like, the median you estimate from those people is close to the true median of everybody in the city. So it's a very like theoretical problem, and I'm going to start with 101 points. I'm going to start with 101 points, and I'm going to take their median. So I generate 101 points. They're between 0 and 1, so the true median is 0.5, and the median for the sample that I got was 0.47. And so I was only off by 0.02. I was pretty close to the actual median. But the question is, with 101 points, how far are you typically, right? Are we typically off by 0.02, or is it more? Is it less? If I wanted to make sure I was within 0.01, how big would n have to be? Those are the questions we're trying to answer. And in this case, because it's all theoretical, I can give you the exact answer, right? I could just like plot, I could do it 1,000,000 times. And so this is what I did, is I did 1,000,000 samples, or what is this, 100,000? I did 100,000 samples of 101 things, and I took the median 100,000 times. And what you get is a histogram like this. So if you do the median of 101 points, 95% of the time it's between 0.40 and 0.597. So between 0.40 and 0.6 essentially. So the 95% confidence interval width is 0.2. So look, this is kind of telling you that if you sample 101 people on the street to give you a random number, you'll be within 0.2 of the real answer 95% of the time, which is quite good. And again, if you're doing this for sums or averages and things like that, you could do all this theory with the Gaussian stuff we did earlier in the class, right? Means and standard deviations. But because it's medians, like how do you do it? It's more complicated. Okay, and there's other ways you can do the theory. But the first question is, we're going to try to throw the tools on validation and cross-validation. We're going to try to do those on this and see what happens. So the first thing I'm going to try the leave one out error. But I want you guys to think about what happens when you try the leave one out error to estimate this. So imagine you just have one data set of 101 points. You calculate the median. The median is remember, what was it? It was 0.478. And we want to understand how far this is from the true thing. So we can try doing the leave one out error. That's what I want you to think about. Question in the front though.
Oh, I thought, like, I was just gonna say the problem with doing the leave one out.
Okay, well, yeah, don't tell me, but because I put it in Mathematize to start you off, and then you can tell me after we get answers. So we're trying to figure out how much variability there is in the median. That's what we want to know. So we have the actual median from our data set. We want to know how far is that from the true value. And we have 101 data points. And we calculate the leave one out error. So what's going to happen? Okay, so I drew on the board a cartoon of what's going on. We have these points, right? There's 101 of them. I only drew like 10. And we have the median. And we're trying to understand the median is not a perfect estimate for the true population median, and it moves around a little bit. We're trying to understand how much it is. And our first try is to do this leave one out error. And so what's going to happen when we do this leave one out error? Let's see what you guys think. Okay, this is a great split. 3, 4, 3. So couldn't be more split. So 3 people think basically nothing at all is going to happen. 3 people think it's going to give a good estimate, and 4 people think it won't give a good estimate, but you can like correct it somehow. So maybe this will help you unlock what's going on. Think about what happens when you do the leave one out error. How does the median move around? What happens? And try to talk to your neighbors and figure out which of these 3 is right. So we have a full spread here, all the possible answers. So take another minute, and I think this, if you draw a copy of this and imagine doing the leave one out error, I think it'll help you figure out what's going on.
So, what do you think that we leave one out?
I said
Not sure.
I answered based on I think
Well, I think it's about the problem.
if the correct factor. I know it won't be.
Maybe you can like
Yeah,
ask him to
it's
explain.
Brian, what's
Yeah.
left over? I'm not sure if it's like I'm not sure if we
No,
can correct by
I
factor,
think
but
you're not,
I feel like we might be
sure
able to,
about,
so I can answer that one, but
the question.
but just
Okay.
on its own,
So,
it won't tell us
okay.
anything.
I want to
It's
clarify,
an
so
actual
it's 101 number.
Right.
Every time you leave 1 out and you have the rest 100.
That's right.
To calculate the median,
That's right.
so you do it,
Hmm?
next time you take this out, you have another rest.
Right.
You
Like-
calculate the median.
You
That's
take
right.
the median
Median
and
one
then you
hundred nine.
multiply
That's right.
and
Got 100
transform it
median.
to, like,
That's right.
Those dots are the 100 medians.
No, those dots are the 100 points. So
Okay.
on the board, I've only done it 0.
Okay, those are the original 101 point.
That's right. Yeah.
Okay, and now based on these even out process,
Yeah.
you would like to estimate the real median of those 101
Well,
points.
so we want to, like, we know the real median of the 101 points.
Yes.
What we want to know is if we were to get a new 101 points, right? Imagine we like paid people money to sample the 101 points. We're going to do it again. How different is that median going to be than the one we just had? That's really what we want to know.
Okay.
So we want to know, like, not this data set is supposed to tell us something about the real population, right? The real
Yeah.
world.
Okay.
And the median of this data set is supposed to tell us something like about the median of the real population, right?
The next round.
Right, exactly.
Sample check.
That's right.
Which sample?
That's right.
Again.
That's right. So, and we want to understand like how close we are. And for things like averages,
Scale.
in the first couple weeks of class, we had this like standard deviation and that,
by
but that only worked for averages. It doesn't work for medians. So this is what we're trying to do. We're trying to understand, can we understand how far is the median from our sample versus the median of the entire population? Can we use these like validation techniques to do it? Or what can we do? Yeah, yeah, no, that's very good.
Thanks. Then I think it should be close.
Yeah.
It should be close.
If you will repeat the last step one time, it is going to be more closer.
Yes.
If you listen to the last step again, so we
I don't know about the answer yet, but I think this close.
Okay, so I'm up to 4 answers, but put in what you think if you change your mind or not.
9 responses in 10.
I think so.
Okay, so we're up to 8. Let's see what people think. Okay, it's still somewhat split. So let's on the board. Let's do this pretend. So these are supposed to be the points. This is the true median. Maybe I'll label this as the true median. And we can start doing the leave one out median by just deleting a point at a time and seeing what happens. And I'll draw those in yellow. So let's see what happens if we delete this point. What is the new median? Well, before this was the middle point. Now, if it was an odd number and this was the middle point, now these are the 2 middle points. So the median changes to here. So this is like median, leave one out, number 1. Okay. Okay. And what happens if we delete this point? Well,
Sorry,
yeah, go
you're estimating median or mean?
the median.
Okay, if it is median.
So if you have an even number, the median is the average of the middle 2, right? So yeah, this is like halfway between this one and this one.
Okay.
Okay. So, so I covered up. If I covered up the first one, that's what I get. What happens if I cover up the second one?
The same.
It's exactly the same thing, right? So the only thing that matters is that this point was less than the actual median. So actually, this is not only leave one out numbered 1, this is leave one out numbers 1, 2, number n over 2, right? The first, all of the ones below the median will do the same thing over here. All the ones above the median, similarly, are going to be on the other side over here, right? So it's going to be median, leave one out, number n over 2 to number n. So I'm going to get these 2 numbers. So what does doing the leave one out tell me? It actually tells me just like how far is the median from the 2 points close to it. That's all it's saying. So it's kind of like the median and the median plus 1 point, the median minus 1 point. So what does that look like as a graph? And this is on the computer. So we look at the medians. So this was the theoretical ones. What do you get? You just get something like this. So the true value for this data set was, the true median was 0.53. And if you run this, you get a little bit less than 0.53, a little bit more than 0.53. I think there's one exception that happens when we delete exactly the median point, right? Then you get the average of those 2 points. So that maybe should be on there as well. So this is median number 2, exactly. So you just get, you kind of get 3 numbers, all of which are close to the median you had originally, 0.53. And if you try to calculate things like the 95% confidence interval, you basically, all these 3 numbers are like exactly the same. So the 95% confidence interval here for this leave one out analysis was 0.03. 95% of the points are within 0.03 of each other. Is that anything like what we were trying to do was get this, right? From the population, if we get a new sample, how would the median change? And here it was like 0.2. So this number of 0.2, this variability from the population, has almost nothing to do with the variability in the leave one out analysis. I think this is the conclusion. And in fact, the median is sort of like famous for being robust, right? The median is supposed to be this thing that doesn't change much when you change a couple of the points. So of course, when you do the leave one out, it doesn't change much. And how much it changed doesn't really reflect how much the median is actually changing when you get a new sample. So what is the moral of the story? The leave one out error is not good for medians. It's not telling you how much the median changes. Okay, let's try the other thing that we learned, which is ordinary validation. So instead of doing leave one out, I'm going to do this. I'm going to have this parameter ptrain, and I'm going to delete like some random subset of the thing, right? So maybe I'll delete 50% of the points and then do the median and see how much it changes. Okay. So that's what I'm going to do, and we can try different p-values. So I'll let you guys decide. What do you think is going to happen when I do that in Mathematize? So we're gonna do the ordinary validation. We just have to choose the size of the validation set and the size of the test set, and we're gonna do it with a set size p. So p is the percentage of the entire set that we use. And your options are: do you think it's going to overestimate the variability of the mean or underestimate the variability of the median? Or does it depend on ptrain? Okay, and this will be the last question we do today. Okay, so basically we're doing the same thing as before, but instead of just deleting one, we're deleting some random subset, right? And now it's more complicated. You can't just like go through all the possibilities because there's way more. So before there were n possibilities, now there's like n to the power of some huge power. So what's going to happen? So let's see what you guys think. So some people think it's going to be an underestimate. Most people think it's going to depend. And indeed, that is the right answer. So here, what I'm doing is I'm just making a training set and a test set by splitting up the x into two pieces, and I'm just doing the median of the training set. And depending on how big you make it, you get different things. So here, the confidence interval is 0.25. That's what the ptrain is 0.5. But if you make it, let's make it 0.1 and see what happens. So here you can see the spread, right? If you make it 0.1, that's deleting a huge number of points. 90% of points get deleted. Then what do you get? Now look at this variability now. Now the confidence interval is 0.5. You basically get everything from 0.1 up to 0.9. If you make a 90%, use 90% of the data, now you're back basically close to what we did for the leave one out, and you have barely any variability, right? And of course, if you do 0.99, that is exactly like the leave one out error, right? Because if you keep 99% of the data, that's like deleting exactly 1 point, and you get like almost no variability. So the problem is, we can't really use this to get the answer to our question either, because it just entirely depends on what you choose as the training, right? And you have no way to know like what's the right one to delete. You can also do with cross-validation. You can try that. So this is trying it with cross-validation. And when you try it with cross-validation, I guess I have to run all these things. When you do it with cross-validation, it turns out you get a number that's too small. So sort of by averaging in the cross-validation, you're getting a variability that's too small. So next class, you're going to watch some videos, and you're going to learn about this thing called the bootstrap. And the bootstrap solves the problem. So I won't say what it is, but I'll just show you the nice plot at the end. So using only one data set, the bootstrap produces something that looks like this, and the variability is 0.18, which is pretty close to what we wanted, 0.19. And so the bootstrap is like the right way to sort of measure the variability in a way that leave one out and cross-validation and stuff don't do. So that's what you're going to watch on Thursday. We'll do some examples with Bootstrap on Thursday, but it's a pretty short chapter. So I think next week we start other stuff. Yeah.
So what was the answer for question 3?
Oh, what was the answer? The answer is it depends. It just depends.
3, not 4.
In question 3?
Yes.
Oh, basically nothing at all. Right. Yeah. So basically, it just tells you nothing about how the median changes. It just tells you how far is the point from the two neighboring points, which don't tell you anything about the median. Okay. So let's leave it there and watch the videos on Bootstrap, and we're going to do some Bootstrap examples on Thursday to see how this thing works. Okay. See you guys.